So now we're going to be talking about some of the advanced features that you can do in OpenVSP with VSPAERO. So earlier we talked about, just the basic features that we have in there. We heard from Dave Kinney about some of the new features that VSPAERO supports, and some of the advanced features along with it. But now I'll show you everything in OpenVSP that you can do. That's a little bit more for advanced users that are familiar with the software. So I'll start by briefly talking about the panel method, which I also touched on in that last presentation. Then we'll just go through the OpenVSP GUI, showing all the different advanced options that are in there. We'll talk about the CP slicer, control surface grouping and deflections, then actuator disks and propellers, which is one of the newer features. So unsteady analysis of rotating blades, which you can see an example of the Uber model there on the right. Briefly talk about the API, and then we'll talk about some of the other advanced features that are not supported in OpenVSP yet, but you can do through the command line, through manual file modifications, things like that. And then we'll finish off with demos for a lot of these advanced features like the CP slicer and control surface grouping. At any time, please feel free to ask questions on the YouTube live chat or on the I/O conference site as well. And feel free to ask if you'd like to see anything in particular demoed, and then we'll try to answer your questions as best as we can. So starting off with the panel method. So this is a slightly more advanced analysis approach than VLM. It takes a little bit longer. Usually not recommended for first-time users. It's usually better to start with VLM. But if you do have things like body components and you're trying to capture more of the full 3D shape, panel method is a preferable approach. So like I mentioned, it's a 3D mesh representation of the geometry generated or represented in a Cart3D file. So we run comp geom to produce that file. You can also run something like CFD mesh and have VSPAERO use that, but it's not a recommended approach. You're much better off just using either the VSPAERO GUI to create that input file for you, or running comp geom to create it. In general, actuator disks aren't included in the panel method approach. They're removed from the mesh. Any thin surfaces are going to be removed from the mesh. And control surface groups are not recommended. These tend to cause problems. Not exactly sure what the behavior is there, but in general, you're better off using VLM if you're going to be using modeling control surface deflections. On the bottom there, the bottom left, you can see that's from the Advanced tab. So that's where you can specify a different dgen geom input file or panel method file. Otherwise, OpenVSP is going to name those files for you based on the name of your VSP3 model. And so if you save your and rename it, those files will be automatically updated as well. Those file specifications are also used when you click the Load Previous Results button. If you've generated VSPAERO results in the previous session of OpenVSP, OpenVSP will look at those file names, look for all the VSPAERO output files associated with it, and try to repopulate the information back into OpenVSP so you can export the results or plot them. Similar, even you could show the VSP viewer as well. So moving on to the Advanced tab of the VSPAERO GUI. First thing on there is the dgen geom input or the panel method input files. They'll activate accordingly depending on if you have VLM or panel method analysis selected on the Overview tab. Below that, you can set the number of CPU, the number of physical CPU cores on your computer. So this defaults to 4. But if you have more processing power available, feel free to use it. This definitely comes into play when you're doing some of the more advanced analysis capabilities, like unsteady analysis of rotating propellers. Those run conditions can take a pretty long time, still a lot faster than CFD potentially, but might as well use all the processing power that your computer has to offer if you can. Batch calculation is an option that's in there to control how OpenVSP runs VSPAERO. So we can either input all the flow conditions at once, which is the default behavior, or we can send the flow condition to VSPAERO one at a time. You can get the results back and read those in. So that will allow you to view results for each flow condition before your entire sweep is finished. So that's what that batch calculation option is. Just different way to run VSPAERO through the GUI. XZ symmetry, recommended if your model is symmetric, should speed up your run case. It's only going to analyze half of the geometry, but it will run faster considering your model is symmetric. So there's the second order Karman sign mock correction option below that. Directly above that, below that first, there's actually a preconditioner that you can change. Its default is the matrix preconditioner, but there's also a Jacobi or a SSOR preconditioner option, and this will affect the speed and robustness. For details about those and the second order Karman sign mock correction, might need to ask Dave Kinney to explain those a little bit more in detail, but feel free to ask if you'd like clarification. Then there's the option to write a 2D FEM file. This is used for structural calculations, like with Beam 3D. Next, below the advanced case setup, is the section for wakes. So you can specify the number of wake iterations. So this is going to impact your convergence and execution time. This is only used for steady analysis, not for unsteady, which is time dependent. Recommend just the default value of 5 is probably a good place to leave it. If you crank it up a lot more, it doesn't really change how the results are converging too significantly, but feel free to test that out and see how it affects your. There's a new option in there for fixed wake, so that's just going to set the number of wake iterations to 0. Below that, we have some other advanced options that are disabled by default. So there's a CO max and a max turning angle option. So those are coarse methods to globally limit the lift from the inviscid solution. There's a far field distance option, so that sets the distance to the free stream. And then there's a ground effect distance as well in there. I believe that is one of the newer options, so you can turn that on to enable a ground effect calculation at your input distance. And what that is going to do is force you to only run a single flow condition, and it's going to rotate the entire vehicle by alpha about your input CG. So next up, we have the right of the advanced tab, starting with the propeller representation. So this is where if you have actuator disks in your model, you can select the actuator disk toggle, or if you have propeller geoms, you could select the rotating blades toggle. Those will activate the disk and propeller tabs accordingly. You can only have one on at a single time, or both of them off. So we'll go into more details about that later. Below that, I have the run mode for stability. So this allows you to do, the first option is a steady stability calculation. So this will run through perturbations about alpha, beta, Mach, and then your, I believe your PQ and R rates as well. And also it will deflect each control surface that you have as well. So this will identify all the different stability coefficients for your input model. You can also run single axis unsteady analysis for PQR. I believe Dave mentioned this earlier in the presentation, so those are there as well in that drop-down menu. For advanced flow conditions, those are going to pertain to actuator disks, unsteady analysis, and some of the stability calculations. You have your V infinity, so you can set the airspeed, and VRef and MachRef are available for hover cases for the most part. That's the use case I'm aware of. So if you set V infinity to 0, you can set VRef to something like rotor tip speed, and so that will allow you to perform like a VTOL hover analysis. Below that you have MachRef and Rho as well, and then you have the REC ref input for Reynolds number along your reference chord. Next we have the CP slicer. So what this does is it sets up sort of like cutting planes that allow you to get the CP distribution about where you place those cutting planes. So you can, first you'll need to activate that CP slicer, and then you can add different cutting slices, set their position and their type. So you can have an X, Y, or Z type, and that'll be the absolute axis that is normal to that cutting plane or cutting slice. You can name them, you could show or not show them. They'll visualize in 3D as a cutting plane. You can also slice the latest ADB file. So that's if you've already run VSPAERO and you haven't changed the name of your model. It's still going to use the dgen geom input name that you've specified under the advanced case setup, but it will use the CP slices that you've set up here to generate CP slice results from that ADB file that's already been written. Otherwise, it'll just run the CP slicer after VSPAERO if you have that activate CP slicer toggle activated. The slicer is actually a separate executable that comes with VSPAERO, sort of like the viewer. So it's run after VSPAERO has already generated the ADB file. If you're running the CP slicer for VLM analysis, it'll show the DCP distribution. If you run panel method, it'll show the CP distribution along each slice. And then in the results manager, we have a tab specifically for the CP slice results. So this allows you to, at the very top left, specify which of those cuts you want to plot. And in the results file from VSPAERO for the CP slice results, it will specify XYZ coordinates and the associated DCP or CP value accordingly. And so since we're plotting it in 2D here, you could specify under x-axis plotting if you want to plot X, Y, or Z on the x-axis, and then your CP or DCP results will always be on the y-axis. You can select multiple flow conditions or just a single. The legend is below that, and then you can also control how you want to scale the axis limits, or you can just leave it in the default to automatically scale those. Hey, Rob or Brandon, I'm not sure if one of your guys' mics is on, but I'm getting some background noise coming in. I'm not sure if that's coming through on the YouTube stream as well.
I am now.
Okay, thanks. So going on to control grouping. So first, which there was a presentation on yesterday, I believe, that talked about subsurfaces and things like that. So if you have lifting surfaces and you add control surfaces or rectangle subsurfaces on the subsurface tab of those geometry types, those will become available in this control surface grouping tab. The first thing you need to do, though, is click the Add button to create a group. Once you do that, all the available control surfaces will show up under the available control surfaces label. You can add those to the group, and you can also, once they're added, you can remove them. The control surface that you select under available control surfaces, that'll highlight red. The once it's added to the group, it will highlight green when you have it selected. There's also a button to just automatically group all of the control surfaces. That's probably recommended for most cases. It'll, if you have a configuration where you have a wing, horizontal tail, and vertical stabilizer, and you have a control surface on each, it will automatically group them into sort of an aileron, rudder, elevator control surface groups. But in general, these groups are set up to act sort of like they could deflect multiple surfaces with a single angle. So each control surface can have an associated gain with it, but you only apply a single deflection angle to each group. So that's where this deflection gain per surface comes into play. That is what is multiplied by the deflection angle that you set on the Overview tab. So you'll first come to the control grouping tab, set up all your control surface groups, and then you go to the Overview tab to enable those groups and set their deflection angle. If you're running a stability analysis, the stability mode of calculation, each control surface group will be deflected or perturbed about, I believe, your deflection angle that you specify on the Overview tab as well. And one thing to note as well, if you have a symmetric wing and you add a control surface, that's also going to be mirrored across to the other side as well. If you want the control surfaces to both deflect in the same direction as you would with an elevator, you'll have to make sure the sign on one of the gains is opposite of the other. So that's what's being shown here, where it's identifying the elevator, each side on the wing, and an associated negative and positive gain for that. Here we have just a basic kind of walkthrough like I just described. You'll start by having control surfaces on your wing. Then you can come to this tab and create a group. You can name it if you like, and then you can select which surfaces you want to place in each group. You can click on those control surfaces under available or grouped to see which one you're dealing with and to make sure you're setting the gains appropriately as you intend. And then you could go back once you set up your control surface groups, go to the Overview tab, set the deflections, launch the solver, and then look at the results to see if those make sense for how you set up those control surface groups. So this is an example of the load distribution for, I believe this is just a wing with a control surface on it, and both are being deflected in opposite directions. So this is creating a roll moment. So now for rotor discs. So first you need to have either disc custom geoms in your model, or you can have prop geoms in the disc mode. I could show that in a little bit, how to change props between disc and blade mode. Then you'll be able to go on the Advanced tab and select the actuator disc representation. That will activate this disc tab where each rotor disc in your input set will be listed. From there, you can set the hub diameter, RPM, CT, and CP for each one. The infinity and row on the Advanced tab, those are going to be applied to all of the discs that are in your set. When you're changing those parameters of RPM, CT, etc. on this disc tab, and you are selecting each one in the rotor disc element setting browser, that will cause each one that you have selected to be highlighted in red in your 3D view. Next, if you have, instead of actuator discs, if you want to represent the actual propeller blades, so you have propeller geons in blade mode, then on the advanced tab you can select, I believe it's rotating blades. So that will activate the propeller tab, and that will deactivate the disc tabs. So this representation, instead of an actuator disc steady solver, this is going to be used with the unsteady VSPAERO solver. So this is going to be a time-dependent analysis. So that's why on the first side, or the top left of this tab, you have a time header. So this is going to default to automatically calculate the time steps based on, I believe it's a 20-degree turn of your slowest rotor for each time step. So it's going to calculate the size of the time step to turn 20 degrees each step. It'll also default to 5 complete revolutions at that time step that it calculates. This is a good, recommended approach. 5 full revolutions to get to a almost steady solution. So if you'd like to use that, it's available. You can just set the number of revolutions and it'll calculate the time step size accordingly. But if you click the auto time step toggle off, then you can actually input the time step size and number of time steps manually. Those will also be calculated automatically if you're in auto time step mode. So you can use that as a baseline of what would be done in the auto time step mode as well. Below that, we have advanced settings. Oops. Oh, I guess the video is going to start playing now. But below that, we have advanced settings, and those are inputs for hover ramp and from steady state, which I think I list on the next slide actually. Oh, there we go. So hover ramp you could use for hover VTOL cases to initialize the flow to help reach steady state more quickly. There's also a from steady state option to initialize the unsteady solver from a steady solution. Then you have below that options for pairing with PSU op for noise analysis. So you can, some DCP Slicer, you can enable it for the VSPAERO run that you're about to launch, and that will be run after VSPAERO completes to generate the PSU op output files. Or if you've already run VSPAERO and you haven't changed the name of your model, anything like that, it can run the noise analysis capabilities on that existing VSPAERO result. So those are the 2 ways to use it there. Below it, you have inputs for the noise type and the length unit that's going to be included in those output files. Then on the right, all of the propellers that are in blade mode are going to be shown in the propeller browser here. You have the option to set your RPM individually for each one. You can set uniform RPM for all of them. Whichever one you have selected and you're changing the RPM for, if you're in uniform RPM, all the other ones will be changed as well to match that. If you have symmetric copies of propellers, those show up in this propeller list as well as separate propellers. So you can, if you'd like, have a different RPM for one propeller versus a different one. That's the symmetric copy of the parent. Also, similar to how disks are treated, whichever one you have selected in this browser will be highlighted red in your 3D view. Once you've run the Unsteady solver with rotating propellers and results are output, VSPAERO will read those different output results and show them in the results manager. The 3 files shown on the Unsteady tab are going to be the history file, the output groups file, not to be confused with the input groups file. So there you set up the single input groups file to run Unsteady analysis. Once VSPAERO completes, it'll output a separate groups file for every set of fixed components and every propeller. OpenVSP will read those in as well and have them available for plotting as well. Similar, each propeller will have a rotor output file associated with it. And so all those are available to be plotted for a quick view in this Unsteady tab. The data that is available for plotting is shown on the top left, and then below it, there's a data type selection option. So like I said, the history, group, or rotor file, you could select each data type there. If you're plotting the group or rotor output files with the group or rotor toggles there, then this group/rotor selection activates below that. So that allows you to select which rotor you want to plot. You could also plot multiple at the same time. Flow condition is deactivated when you're running an unsteady analysis. You're only allowed to do one flow condition at a time. So it just shows you there which flow condition you ran that result at. There's a legend below that, and then, like all the other tabs, you always have a manual axis limit control feature. The other results from the Unsteady solver that I read in are the per blade load distributions. So we still have the .load file that VSPAERO outputs, but when you're running Unsteady analysis with rotating propellers, we also have a rotor output file for each propeller that includes the distribution of forces across each blade. I believe they're averaged across the entire set of time steps, and those are available for plotting here. So similar like the Unsteady tab, you can select between plotting either the load distribution file or the rotor file, which is that blade setting, and then you could select which blade you want to plot. So this slide is just describing some of the capabilities of that OpenVSP provides through the API to run VSPAERO. So I'll talk about the details of OpenVSP's API, how to use it, the documentation for it, things like that. But this is just what is available specifically for VSPAERO. So the way that VSPAERO is run through the API in OpenVSP is through what we call the analysis manager. So that allows you to basically use all the same functions to set up and execute different analysis tools without needing a specific function for running VSPAERO or running mass properties. We use the same functions but different input strings to tell the analysis manager which tool we want to run. So for VSPAERO, we have a VSPAERO compute geometry analysis, so that will generate your input geometry representation, so the dgengeom or panel method file. Then we have a VSPAERO single point analysis or VSPAERO sweep analysis if we're doing a single or multiple flow conditions. Once VSPAERO is launched through the API, the results are read back in and stored in the results manager. That's also why we call the GUI that plots all the VSPAERO results the results manager. So you can grab various results through the API from the results manager and do it with them. There's an example here on the right of us running a sweep, tessellation sweep through the API and plotting the results and showing how those compare to lifting line theory and AVL results. This example was from the master VSP VMV script that was written a little while back. Probably the most complex script example that is included in the API scripts directory that you can see when you download OpenVSP from the website. It's quite long, just runs VSPAERO hundreds and hundreds of times and generates all these different results, but does demonstrate the advanced automation and data analysis capabilities that you can do just with AngelScript. There's a couple of other examples in there. The CP Slicer example. There's a script that shows the different analysis types that we have, and then there's also one that shows how to set up the Unsteady solver with rotating propellers and execute that. Another that shows both how to set up actuator disks through the API and control surface groups through the API. These are all VSP scripts, but they translate pretty much one-to-one to a MATLAB or Python, so should be able to follow them pretty well if you are familiar with how the API is used. Recently, there's also a SweeptWing API example that was added. I believe it's in the VSPAERO example directory, so you could take a look at that. It's also available on, if you go to GitHub. It's formatted, I believe, in Markdown format. One more thing to actually add on that last slide. I believe we're going to send out all these slides so everyone can click on these links, but there's API documentation for the different actuator disk and propeller functions and the control surface group functions that you could click on, and it'll open up the latest API documentation. So the last couple of things on here are features that currently are not supported in OpenVSP, but you can still run through the command line or by modifying VSPAERO files yourself. One of them is this number of survey points option. So you can add XYZ coordinate points of, I believe, where you want to query the flow velocity. That requires a modification of the VSPAERO input file. So also, you can do isolated rotor analysis, and there's actually an example of that in the VSPAERO_EX example directory. So take a look at the isolated rotor example. What that does is it rotates the entire frame about a single rotor instead of rotating the propeller itself. And last, Dave Kinney talked about this a little bit, and this is something that we may add more support to the OpenVSP GUI in the future, but right now, if you want, you can modify the groups input file to specify arbitrary complex motion with input velocity and acceleration vectors and mass or the inertia matrix. But like I said, you have to modify the groups input file manually. But these are some of the capabilities that you can do through the command line if if the OpenVSP GUI is not supporting it. So I'll pause for a quick minute and see if there's any questions, but if not, then I'll demo some of the things that I just talked about here.
There have been quite a few questions, but I think we've been able to address most of them on the fly, Justin. So
great.
I'll let you know if any pop up here, but you can probably go ahead and go into the demo.
Okay, great. Thanks.
One particular request was to do a demo of the stability analysis and then maybe pull up the stab file.
Yeah, okay. Sounds good. So hopefully everyone can still see my screen okay. Pulling up the latest version of OpenVSP. And just to make things easier and not spend time on simple modeling, I'll just pull up an example that I have already of a pod, a main wing, horizontal tail, and vertical tail. Very simple example. Tessellation is a bit high on this one at the moment, so just for the sake of time, I'm going to crank things down a little bit. Okay, that should run much faster now. The first thing I'll show is I added control surfaces already to this. That's done on the sub tab for each wing geometry. And so I can go ahead and delete it. And if I'd like, I could just come in here and click add. I won't go into the details of the different parameters that you can use to model these control surfaces, but this is where you would be doing it. Then if I go into VSPAERO and I go to the control surface or control grouping tab, notice nothing's here. I'll have to create a group first. Then all the available control surfaces will pop up. Each one I click on will highlight red. And so if I'd like, I could call this something like the aileron group. I could add the 2 control surfaces on the main wing. You can use the shift and control keys to highlight multiple at a time. Added, see how they change to green. Next, I could add another group for the elevator. So that would be the horizontal tail. And here, what I want to do is set one of the gains to -1. I'm going to do that for the symmetric copy, which is going to be this bottom one here. And then last, I'll add another group for the rudder. If I didn't want to go through all that manual adding of control surface groups, I could have just clicked the auto group remaining control surfaces button, and that, I believe, would have set it up exactly how I set it up here. Now, if you notice on the overview tab, we have control surface angles for each one. So I could do something like a 5-degree, maybe a 10-degree, something like that. I'm just going to run a single flow condition so I can demonstrate how this all works with the stability calculation option. I'm going to decrease the number of wake iterations just so this runs a little bit more quickly. And now under stability type, I'm going to change to steady and click launch. And so what this is going to do is run the input flow condition, then it's going to perturb alpha, beta, Mach, all the different control surface groups, and also the, I believe, roll pitch yaw rates as well. This might take a little bit of time, but I could look in the folder that was running OpenVSP and explain the additional file that's output when you run a stability calc, and that's the .stab file. So I could open that up and show you guys what's in it. But you'll see here what it did was perturb the base. It ran the base arrow, then it perturbed alpha, then beta, then there were different roll pitch yaw rates, Mach, and then it went through each control surface group and perturbed them by 1 degree from whatever you had as the input condition. So that's what this is showing here. And then from that, these coefficients with respect to each of those perturbations can be calculated, and those are all shown. And also at the bottom, we list the static margin and the neutral point. But these are all read to OpenVSP. You could plot, I believe, just export them. I believe you could plot them as well. I need to double check that one. But so that's what's in the stab file. So that's kind of the basics of both control surface grouping and stability calcs. I'll turn this back to
Before you
stability calc.
Go ahead and launch the viewer, and you can show them all 10 or 11 cases or however many ran.
Yeah, good point. So I will show the pressures in a little bit. And what we could do here is show the trailing wakes. We could then show the control surfaces. One thing to be aware of, sometimes the control surfaces just might look a little bit funny in the viewer. Might not line up exactly with how they're modeled in OpenVSP. Believe for most cases it's just an artifact of the viewer, so nothing to be worried about, but just something to be aware of. Now let's see. Could draw the control surfaces deflected. You'll see the aileron is deflected there. The elevator should be deflected a bit as well. And then that's showing the base aero run case. I could then go through and step through each one. I'll turn on the smooth function shading feature that Brandon showed earlier. Some other options, you could show points instead of lines, things like that. But you could step through each case. There's yaw rate, and then here are the different deflections. All right, so next show is about the CP slicer. So for this one, I'm just going to go ahead and remove the control surfaces. I believe you can have CP slices with control surfaces, but just to prevent any issues, I'm going to leave it off for now. But I believe it should work without problem. So what I'm going to do is come into, let's see, the Advanced tab, and if I look at CP Slicer, I could first hit Add Slice, and this is going to be a slice that fits within the bounding box of your entire geometry set. So if you just have a wing, it'll just slice the wing, but if you have a tail, anything else, it'll extend all the way to that. You can change the position. Oops. If it's moving too much, you can click these buttons to make it a little bit easier to slide around with more fine control. You could turn that visualization on or off, change the axis of the normal axis of it. And if I wanted to, I could slice the latest ADB file, but in this case, I'm just going to run this again. Oops. Oh, you'll notice these groups aren't deleted when there aren't any control surfaces in them. I'm just going to go ahead and remove them manually. I don't believe it would have caused any issues, just since there's nothing even in them, but just something to look out for. Go ahead and launch the solver. Now the CP Slice tab is activated, and that is going to show you at this slice what the DCP distribution is.
You probably want to click the flip y-axis button.
So, yeah, this one's a little bit strange. It's kind of just not exactly, it's pretty much just showing the, is that just flipping the sign on the results?
Yeah, it's traditional to plot negative CP instead of CP.
Okay.
Why don't you run the same case in panel mode?
It'll take just a little bit longer to run, but still pretty fast. Now, if you look at the DCP Slice tab, now you're showing shows the upper surface and the lower surface. So along that volume instead of just the 2D solution. If you have more than one slice, you can select individuals, multiple, same thing with flow conditions. That's available as well. Here, if you want to see the distribution along a different x-axis, you can do that as well. So what I'm going to do next is change back to VLM. Unless there's anything anyone would like me to pause and answer real quick, but I was going to show actuator disks and propellers next, because we are kind of running out of time. So
that's great. Keep going.
Okay. So let me delete the mesh geom, show these again. I'll quickly add a prop. Make this much smaller. 7. Move it a little bit away from the nose. And first I'll show actuator disk mode. So I'll change this to disk. You'll see that becomes a 2D disk. Where'd the VSPAERO GUI go? So next thing, I'll come to the Advanced tab. I'm going to deactivate the CP slicer, and I could even just delete that slice for now, so it's not a focus of this demonstration. Propeller representation, I'll change that to actuator disk. Now, if you'd like to change it, you can set your V-infinity and rho. I'll leave it just as the default. I'll go to the disk tab, and now you can set RPM, CT, CP, however you like. I'll just leave the defaults for now, and I'll click Launch Solver. Great. And I could launch the viewer. And now, if you go to, I believe, arrow, you can click on rotors. That'll show that actuator disk. Good trailing wakes. You could see how that affected the solution. So it's just a quick. Sorry, getting some feedback. Rob, is that your mic on? Hearing myself through something. All right. Well, yep. I think that works. Now I can't hear myself, so it's good. Last thing I'll try to show real quickly is the Unsteady solver. So the propeller tab with rotating blades. So I'll change the prop to blades mode. And now if I bring the VSPAERO GUI back up, and oh no. Well, not sure what happened there. Sorry about that. Didn't like something in the GUI. Not sure what, but I'll try to pull this back up quickly. Let's get rid of those again. Delete. And let's add a propeller again. All right. Now if I go to analysis, VSPAERO, you can only run a single flow condition at a time when you're doing unsteady analysis with rotating propellers. Now I could click this rotating blades option. Same sort of thing as actuator disk. You can set your advanced flow conditions if you'd like. You'll notice number of wake iterations deactivates because this is a time-based analysis. Go to the propeller tab. You can change your RPM. And while I change that RPM, you'll notice that this size of the time step is changing because that's being automatically calculated for you, which I believe is 20 degrees of rotation for each time step. I'd have to double check that though. I'm just going to run this for 2 rotations to keep it somewhat fast. And let me decrease the tessellation real quick just so it doesn't take too long to run. 1 second here.
So while Justin's working on his tessellation settings, some folks have asked about setting up counter-rotating same axis propellers. So I set up a case to run kind of while we were doing this. It's the example rotor case. I set those up to be rotating same speed, opposite directions with a small deflection. And you've got the lead propeller, and then the aft propeller is getting some unsteadiness in the results. And the solution looks a bit like this. So yes, it will run. I'm not sure how much we could actually trust those results, but it will do it. So there's that. So Justin, I apologize for interjecting there. And
oh no, I'm glad you did. Yeah, this solution's taking a little bit longer than I would have liked. Hopefully it won't take too much longer though. I could real quick describe the kill solver button if this was taking too long and I wanted to change some settings to update it so it will complete in a shorter time by changing tessellation, things like that. You could click the kill solver button and redo things. I could pull up, unless there's any questions you would like me to answer, I could pull up real quick and show the input file that's being run. So what this is doing is, or OpenVSP is doing, is it's modifying a groups file to go along with the VSPAERO input file and the dgengeom input file. And what that's doing is basically just setting up your fixed components, which is going to be your wing, your body components, everything like that. And then it creates a group for each propeller, which in this case we only have one. You'll notice that there's all this other information for velocity, acceleration. That is something that I believe you can edit manually right now. And there will be more support for it in the future through VSPAERO. But at the moment, there's nothing in the GUI to set that inertia matrix or change some velocity of different components. So that's what the group's input file is. Now,
to be fair, back in the day, there was no GUI support whatsoever, so it's come quite a long way.
So yeah, other than waiting for this solution to run out and then pulling it up in the viewer and the results manager, that's pretty much all I had, and looks like all the time that I had available as well. So are there any questions I could answer in the meantime?
No, that was really good talk, really good demo. Rob?
Yeah, we've been able to answer questions online, so I think you're okay. There are another 5 minutes here, so we can just let this run. I don't know if it's going to quite finish, but
I think if you kill solver, you can still see the results up to that time step, but that
can you?
may be mistaken.
I don't know about
that. Well, one thing I could just demo in a separate window real quick is that new load previous results option. So if I open up a new instance of OpenVSP, go to VSPAERO, and I look, it's going to default to unnamed dgengeom. If I have run VSPAERO with an input file called unnamed dgengeom and click load previous results, it'll just go grab those results from the folder that you're in and repopulate them. So this is a newer feature that was added. Hopefully it's helpful to some people. That's just a quick demo of what that does. It doesn't work for all VSPAERO results. So if you're trying to read in a result that was generated, way back when, it might not work correctly. But it definitely will work for any results that you generate in the latest versions of OpenVSP.
And that feature, it doesn't just work for empty models with untitled. If you save your model in a directory and you ran VSPAERO in that directory, all you have to do is go back, open that VSP3 file, and then when you say load previous results, it'll find the most recent one that corresponds with that model.
Exactly. And it works for the viewer as well. So if the viewer can find your ADB file, it will open it.
And someone just asked if it would also load if you run from the command prompt. And yes, it will. If you run from the command prompt and then you go to that directory, open the VSP3 file and say load previous results, it will reparse the files, pull them into the viewer, the results manager, and the viewer.
Exactly. So it looks like this might finish. Sorry, this is taking a little bit longer than I expected. But I think we'll be able to show it real quickly before the next presentation. All right, just about done here. Of course, I am running this on a very old computer too, so hopefully it'll be a little bit faster if anyone else tries the same model. All right, there we go. So real quick, pops up the Unsteady tab of the Results Manager. I'll just show the really cool features of the viewer. So I'll plot the pressures, and then I will also show the trailing wakes. And now instead of stepping through flow conditions, I'm stepping through time steps. And you could see the wakes growing off the lifting surfaces. And that's a relationship of your V infinity input and your time step size. And the propeller is rotating in those wakes off the trailing edge are shown as well. So pretty cool stuff. I think that's all I have time for, but thank you all for listening.
Thanks, Justin. Really great stuff. Appreciate all the work that you've done trying to get the VSPAERO features implemented in the GUI, and looking forward to all the continued work that's coming down the way. So thank you again.
Yeah, no problem. Thank you.